One of the unforeseen realities of being an astronomer is I spend a lot of my time saying things like, no, that isn't caused by aliens. Yes, relativity is real. No, I don't do cosmetology, I do cosmology. And yes, we really did land humans on the moon, and yes, it is weird we haven't gone back yet. It's a weird job, y'all. And today, at the start of the show, I'd like to head things off by saying no. It doesn't look like the Earth is going to get hit by an asteroid on Valentine's Day 2046. As we'll discuss in today's closer look, a new asteroid has been discovered with an orbit that crosses our own planet's orbit. In general, this object and Earth are very good at not trying to occupy the same space at the same time. And we've managed to coexist for a fair amount of time. We're going to have a close approach, however, in 2046, and for the first time in a long time, the potentially dangerous asteroids list actually gave us something to worry about. In today's closer look, we talk about that little asteroid 2023 DW and why we may not need to worry about that one space rock. But we do need to be prepared to worry about a future space rock. Along the way, we'll also look at robots, supernovae, misplaced baby stars, and so much more. All this and more is coming right at you now on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. In the past few years, advances in computing and materials science have allowed robots to enter new and exceedingly complex realms. From tiny camera bots that explore fallen buildings to back-flipping factory bots from Boston Dynamics, it is starting to feel like anything is possible. In new research from Antarctica, researchers have even sent robotic cameras under a glacier. This exceedingly dangerous environment is one researchers need to explore so we can better understand climate change and predict sea level rise. And now one little robot has gone there. Developed by Brittany Schmidt, this bot is called IceFin, and it is able to explore within and beneath glaciers. In 2019, Christina Halb led an expedition to the Ross Ice Shelf and released IceFin to explore the interface of water and ice. Getting into the glacier wasn't as simple as looking for exposed water. The team had to bore through the ice using hot water, and they lowered in the 12-foot-long, 10-inch-wide robot on a tether. During 3 dives, IceFin explored 5 crevasses as well as the sea floor, returning images and data on everything from temperature to pressure to salinity. This data is strangely beautiful and captures the interplay between ice formed from snow, sea ice, and sea water. They also imaged how the ice has shaped the seafloor along the ice flow's path. According to a summary of the research, which is published in Nature Geoscience, quote, "The team observed diverse ice features that provide valuable information about water mixing and melt rates. They included golf ball-like dimples, ripples, vertical runnels, and the weirder formations near the top of the crevasse, globs of ice, and finger-like protrusions resembling brinicles." End quote. The techniques used by IceFin and its research team don't just tell us about our world. They also help us practice for future exploration of ice-covered water worlds like Europa. IceFin is funded by NASA's program, Planetary Science Technology from Analog Research. IceFin is a tremendously powerful explorer, but it is neither navigating autonomously nor is it swimming without a line. With its tether sending data back to its team, it could only get as lost as its handlers let it. Future robots are going to need to do better. They are going to need to go wireless and explore autonomously from other worlds where time lag makes it impossible for humans to steer their journey. And if you've ever watched a Roomba, you know these future explorers will need all the help they can get. And researchers from the University of Arizona have taken a lesson from the children's story Hansel and Gretel and are using tiny sensors as breadcrumbs to mark their robot's path. In a new paper in Advances in Space Research, researchers led by Wolfgang Fink detail how a parent rover will deploy child explorers into Martian or other worlds' caves, and the rovers will drop a small sensor whenever they sense the signal from other sensors getting too faint. By deploying based on signal being received instead of by distance traveled, the system will be robust against issues caused by different signals not carrying consistently in different areas. This is like how Bluetooth may carry different distances through different parts of your home or apartment. These sensors not only will facilitate navigation, they will also act like communications relays, allowing the explorer's data to jump from sensor to sensor back to the parent rover through the system's mesh network. Cave exploration is something I can't wait to see happen. It is entirely possible that Martian caves will provide protection from radiation and access to ices both for future human explorers and maybe even for ancient microbial life that has managed to eke out an existence since Mars' climate collapsed. I, for one, am eager for our robot overlords to create their Martian mesh networks and beam back images of whatever may lurk in caves on the red planet. It is beyond the imaginations of most of us to envision just how much the worlds in our solar system have changed since they first formed. Luckily, thanks to a new computer model published in Science, for the Earth at least, we can simply watch a video. This work, led by Tristan Salz, does more than just show us how the Earth's tectonic plates have shifted past each other. It also shows us how rivers, global-scale erosion, and sediment deposits all work together to constantly shape and reshape our planet. This is a first-of-its-kind model that combines geodynamics, tectonic, and climate forces with surface processes. This video looks at the Earth in 10-kilometer pixels and in 1 million-year time steps. This team's findings will provide a dynamic and detailed background for future scientists in other fields to test their models, such as biochemical cycles or biological evolution. Humans aren't something we can readily factor into our climate models, however. But more and more, we are finding evidence in other places, from tree rings to sedimentary layers, pointing out how we have changed our environment over time. New research here in North America shows that in just the last 11,000 years, our modern deserts have emerged from a once lush American Southwest, and the temperate rainforests of the Pacific Northwest have grown from once arid landscapes. The Halcyon era, which started 11,000 years ago, is defined by the end of the last major ice age, but is often referred to as the Age of Humans. This is because our major archaeological sites and records were largely laid out during this period, and our shaping of our landscape literally has reshaped how our planet works. A new paper in the journal Climate of the Past with lead author Hannah Palmer pulls together the results of 40 studies to review this change. The review finds 11,700 to 8,200 years ago, there were warm seas, a warm, dry Pacific Northwest, and a warm, wet Southwest with little fire activity. From 8,200 to 4,200 years ago, the pattern reversed as the ocean's surface cooled. For the past 4,200 years, the climate has been highly variable, with fire activity peaking in the past 2 centuries due to human activities. As Palmer puts it, quote, "Humans have been living here throughout the entire Halcyon. The climate impacted them, and they impacted the climate, especially in recent centuries. This paper shows how that push and pull has changed over the past 11,000 years." End quote. And maybe, just maybe, understanding the past will help us shape the future. After the break, we're going to jump from looking at our world's evolution to looking at stars behaving weirdly. Stay tuned. Living inside the Milky Way galaxy offers observational astronomers both benefits and frustrations. On one hand, everything is close enough that we can make out details when we have a clear view. On the other hand, everything is getting in the way of seeing everything else. It's a star block star, explode, cloud, interrupt with dust kind of galaxy out there. For more than a century, astronomers have been trying to map our galaxy from our position halfway out from the center in an attempt to piece together the shape of things by mapping out somehow enough details. Various optical surveys have mapped stars and allowed us to learn we live in a barred spiral galaxy. The issue is, our galaxy is a lot more than just stars. And let's face it, a lot of stars are hidden by dust and gas. In a new study in the publications of the Astronomical Society of Japan, researchers have turned from mapping stars to instead mapping the clouds, the giant molecular clouds that can form stars. The work was led by Shinji Fujita, and it used the 45-meter Nobiyama radio telescope to look for light from carbon monoxide molecules in the cold clouds of space. Their survey looked at just one quadrant of the Milky Way, but that one corner contained 140,000 molecular clouds. These clouds were mapped out by software that was trained to find clouds using data from the WISE telescope, and that has the ability to sort clouds as near or far. According to Fujita, quote, "The results not only give a bird's eye view of the galaxy, but will also help in various studies of star formation. In the future, we would like to expand the scope of observations with the Nobiyama 45-meter radio telescope and incorporate radio telescope observation data of the sky in the southern hemisphere, which cannot be observed from Japan, for a complete distribution map of the entire Milky Way." End quote. This is an amazing start, and I can't wait to see what future observations reveal about our galaxy. While it is a struggle to get a solid perspective on what's happening in the outer parts of the galaxy, we are pretty good at seeing into the core of the galaxy. And as we're learning week after week, that's where the galaxy hides the weird stuff. In a new paper in the Astrophysical Journal that is led by Florian Pesker, researchers identify a young star, only tens of thousands of years old, that is cocooned inside a dust cloud as it orbits ever closer to our galaxy's supermassive black hole, Sag A star. Cataloged as X3A, this baby star is anything but tiny. Its mass clocks in at about 15 times the mass of our sun. This is a hot young star that formed from a massive amount of material, and it did not form where we see it today. According to Pesker, quote, "It turns out that there is a region at a distance of a few light years from the black hole which fulfills the conditions for star formation. This region, a ring of gas and dust, is sufficiently cold and shielded against destructive radiation. End quote. This young star's orbit carried it out of the safety of that ring of dust and gas, and now the star spirals towards the danger zone where Sag A star can start to tear away X3A's dust and perhaps one day tear apart the star itself. Unless, of course, X3A self-destructs first. Massive stars are very short-lived. Exactly how they die depends on how much mass they lose during their life. It is entirely possible this young star will one day explode as a supernova. It might also just sputter out to form a white dwarf if it blows off too much mass. For now, though, X3A is a growing toddler, and it is continuing to draw in material. Observers can see hot clumps near the star which could become X3A's next meal. No matter how X3A dies, this star is going to send off material that will stream toward Sag A star, where it will create a spectacular fireworks show as the particles scream out in high-energy light as they stream toward the black hole's event horizon. Massive stars like X3A don't form exactly like smaller stars. With a star like our Sun, material in a collapsing cloud flows towards the center until the pressure from the forming star's light pushes back and slows the protostar's growth. This kind of a lazy inflow of material can't build stars fast enough to make the massive stars we see shining in the sky. These stars need to eat clumps of material to reach the sizes we see. While we see stars with clumps waiting to be consumed, and we certainly see massive stars, we hadn't seen massive stars actively eating clumps and experiencing episodic bursts of growth. At least not until a team led by Ross Burns combined the powers of numerous radio telescopes to observe the young star G358-MM1. The resolution of a telescope is directly linked to its size. If you combine the light received by telescopes spanning our planet, you can effectively get a planet-sized telescope. While technology still won't let us do this with the colors of light our eyes can see, we have mastered combining radiolight to get high-resolution views on everything from black holes to star formation. By using this technique called interferometry to look at G358-MM1, researchers could make out a four-arm spiral with clear rotation. Per their press release, quote, "Spiral arms in rotating protostellar disks are a sign of instability, a characteristic which was long theorized to be associated with massive star formation, but had yet to be proven observationally." End quote. Put another way, they saw exactly what we expected. This is the hot, turbulent star-building process we had modeled. This is only one set of data on one star, but it is a start. This team has proven this kind of observation is now possible, and we can look forward to more of this kind of data. Understanding stellar evolution keeps proving a bit harder than it should. If a star conveniently forms, lives, and dies in relative isolation, things are pretty easy to understand. The star would have a given mass, which would cause its core to have a given pressure and temperature, and physics will lay out how elements should form through fusion and how the star should, more or less, end its life. Composition, rotation, mass loss, and magnetic fields all add levels of uncertainty and cause one star to vary from another. But the big picture story for isolated stars is one we understand. Not isolated stars, which is a whole lot of stars, those are a lot harder to sort. two stars orbiting one another can actually pass mass back and forth like people on a yo yo diet sharing a wardrobe. With the most massive stars, the ability of one star to devour mass off the other can lead to explosions that fizzle and even give them a second lease on life. Case in point, supernova 2018 IVC. Located in the galaxy M77, this supernova radically rebrightened after it had theoretically blown itself apart. The initial explosion was spotted on October 24, 2018. For the following 200 days, researchers used the Atacama Large Millimeter Array to observe the light fade as the shockwave expanded and the system cooled. This work is published in the Astrophysical Journal Letters and is led by Kichi Maeda. Normally, during this expansion and cooling process, the shockwave from the supernova slams into surrounding material that the once massive star flung off when it was younger. The thing is, the team monitoring the supernova never saw the characteristic shine from the shocked material. So they kept watching and watching. And 1,000 days later, things finally brightened up. These observations imply that the star, as stars do, must have shed vast amounts of mass, and then somehow that mass got swept away, leaving the region around the star empty. Computer modeling indicates the star that went supernova underwent a period of extreme mass transfer about 1,500 years ago. More than 5 solar masses of material was transferred from the star to a companion, leaving the original star only 2 solar masses in size and surrounded by basically nothing. This combination means we saw the supernova explode very much like an isolated star would explode. But how the supernova evolved was actually dictated by that companion. This is just the second supernova to be observed displaying this kind of behavior. But as the study authors point out, observations like these are still extremely rare. Here's to hoping more of these weird objects are spotted and more teams can get telescope time to watch them evolve. The only way we're going to fully understand all the weird ways binary stars evolve is with more data. The need for more data is one that has been recurring throughout this show. One of astronomy's emotionally more challenging tasks is deciding what science does and doesn't deserve telescope time. There are so many things we want to know, but there are also things we need to know, like, is that newly discovered asteroid going to hit us or not? After a break, we're going to take a closer look at the search for dangerous asteroids and NASA's efforts to prepare to move them out of the way. Stay tuned. There is an entire genre of fiction dedicated to stories of infalling rock trying to wipe out life as we know it. I can't be certain, but as near as I can tell, the first such story was Jules Verne's Off on a Comet. And the best of this genre, in my opinion, is either Larry Niven's Lucifer's Hammer or Neil Stephenson's Seven Eves. In each story, there is a moment of, what's that thing in the sky? A lot of these fictional depictions get one thing very wrong. We can't just look at an asteroid and know it is going to strike the planet. To calculate an orbit, we have to make image after image and see how that spark of moving light changes in position and brightness over time. And then we have to perform complex calculations that model how our world, that rock, and all the other major gravitational masses in our solar system will move and pull on one another over time. This delay between, what's that? And getting a rough prediction of motion and getting an accurate prediction of motion can lead to periodic excitement. Back in 2004, there was a brief window during which there was a 2.7% probability that a newly discovered asteroid might hit the Earth in 2036. And even if it missed in 2036, there was a possibility it could come back and strike us in 2068. This kind of an impact wouldn't necessarily end civilization as we know it, but it wouldn't be good. Luckily, further observation showed that asteroid, now named Apophis, is absolutely not going to hit us in either 2036 or 2068. That asteroid is just over 300 meters across and has an orbit that regularly crosses Earth's orbit. In general, Apophis and Earth are in very different places around the Sun. In 2029, however, Apophis will pass between Earth and our geosynchronous satellites. But that is the nearest approach we can currently see in our future. I'm telling you this story because, as I said at the beginning, another potentially dangerous asteroid has just been discovered. Cataloged as 2023 DW, this 50-meter wide asteroid at the time of our recording has a 1 in 607 chance of hitting Earth on February 14th, 2046. On NASA's standard risk scale, it has a Torino scale value of 1, which translates to possesses no unusual level of danger, and the chance of collision is extremely unlikely with no cause for public attention or public concern. Except there's social media, so there are people out there making other people concerned, so I'm doing this story. Anyways, when you see someone panicking on social media, you need to know we are still figuring out all this asteroid specifics, and based on what we know so far, there is no reason for concern. And the only reason for excitement is nearby flybys of asteroids make for really cool images. Come 2046, we can expect all kinds of observing to take place. And no lies, while writing this article, I decided I need to travel in 2029 to be somewhere that I can watch Apophis threaten satellites. Australia looks kind of good. So far, we've been lucky. There are countless telescopes used all over the world, night after night, to try and discover new asteroids. And they are constantly finding new cool rocks orbiting our sun. Every once in a while, a project like Atlas will spot a couple meter across object about to harmlessly light up our atmosphere. Every decade or so, we'll spot an asteroid that looks like it could hit, but follow-up observations just keep showing that object of interest won't hit. But what if an asteroid was going to hit? What would we do? Space and science organizations around the world regularly fund projects designed to test techniques for moving asteroids. And this research is informed by the latest discoveries made by spacecraft sent out to visit asteroids. In the early 2000s, we imagined asteroids were mostly solid objects that we could potentially push out of the way by either mounting engines on the asteroid or exploding bombs next to the asteroid to push it with shockwaves. Unfortunately, missions like Hayabusa 2 and OSIRIS-REx are finding that asteroids are anything but solid in many cases, and putting engines on an asteroid might just lead to engines burrowing into an asteroid. So, what do we do to prepare to deflect a rubble pile of rock that is orbiting like so much dumped gravel? Well, if we're NASA, we practice moving things we can't accidentally send crashing into the Earth. Back in 1996, astronomers using the Kitt Peak 0.9 meter telescope discovered a small, roughly 800 meter across asteroid on an orbit that dances back and forth from about Earth's distance from the Sun to 2 times Earth's distance from the Sun. This asteroid was named Didymus, and over time it was realized Didymus has a moon. And in 2017, NASA approved development of a spacecraft that would smack that moon. That mission, the Double Asteroid Redirection Test, or DART, wanted to see how the orbit of Didymus's moon would change if we crashed a 610 kilogram spacecraft into it. We knew Didymus would hold onto its moon, and there was no danger we'd send that moon into an Earth wrecking orbit. The only thing destined to seriously change was the moon's orbit around and around Didymus. That moon, by the way, is officially named Dimorphos. But a lot of us got in the habit of calling it Diddy Moon before it was named, and we remain sad that Diddy Moon didn't become its official name. Anyways, on September 26, 2022, as Didymus and its moon passed near the Earth, the DART mission smacked hard into Dimorphos, a rubble pile asteroid. The details of what happened aren't well known, but we do know the mission caused a many hundreds of kilometer-long tail of dust to form behind the moon. To quote the NASA image caption, these images, quote, captured the breakup of the asteroid Dimorphos when it was deliberately hit by NASA's 1,200-pound Double Asteroid Redirection Test Mission spacecraft on September 26, 2022, end quote. The moon is still there. We still see it in orbit. It is, in fact, orbiting 33 minutes faster than it was before. We hadn't anticipated this large of a change. What we're seeing is conservation momentum at its most fabulous. DART struck the moon and transferred all of its forward motion into the moon. This would be like a pool ball hitting another ball and sticking, causing both objects to move forward together. Except in this case, the balls didn't stay intact. Instead, chunks got flung away, and for every rock, pebble, or mote of dust that got flung behind, the moon got pushed that much forward. Because this was a destructive collision, we got to see an amazing amount of motion. This is the kind of asteroid deterrence you'd never want to use near the Earth. If an asteroid were to be shattered near our planet, it could potentially create a ring of destruction as our world rotates and gets hit by piece after piece. But if this is done just right and done far enough away, this could be an effective way to move an asteroid into a new orbit that keeps Earth safe. And this is just the first of what will hopefully be many tests of many different ways to potentially move asteroids. In addition to pushing asteroids through impacts, engines, or explosives, researchers are also considering using gravity tugs, where a high-mass object with engines is placed near an asteroid and uses its gravity to slowly pull an asteroid into a slightly different orbit. We are also looking into painting asteroids white, so the reflection of sunlight can actually push an asteroid away. We have lots of ideas, and there are lots of asteroids to practice on. Test 1 is complete. No dangerous asteroids are currently on the docket. It is time to find some funding and paint some asteroids white in the name of science. After another break, we'll be back to battle dust, look at launches, and contemplate how to keep time on the Earth's moon. Stay tuned. I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launch Pad. Hey, Eric.
Hi, Pamela. There was a huge variety of rocket launches this week from the US, New Zealand, Kazakhstan, and China. And there's one less soil in space now. As we were recording last week's show, SpaceX launched a batch of satellites that provide high-speed internet service. At first glance, that's not particularly unusual. However, this time, SpaceX sent a batch of satellites up for OneWeb, a satellite internet constellation owned by the British government, and Starlink's biggest rival. Launched on March 9th, this was the third launch SpaceX has conducted for OneWeb. Over the course of about 95 minutes, starting 1 hour after launch, the OneWeb satellites were deployed from the second stage in pairs. The first stage returned to Landing Zone 1 at Cape Canaveral Space Force Station in Florida after launch. The astronauts of SpaceX Crew 5 returned to Earth on March 10th. The capsule Endurance departed the ISS late Thursday night and spent the next 18 hours aligning its orbit for return off the west coast of Florida in the Gulf of Mexico. The orbit and splashdown were nominal, and the reentry was precise enough that the recovery vessels had the capsule in sight while it was still miles up in the air. The crew only had to wait a few minutes for the recovery boats to attach a lifting harness to the capsule and be raised on board the ship. The 4 crew members were given a quick medical checkup, and then they were rushed back to the Kennedy Space Center, along with some experimental samples, via a helicopter which landed on the recovery ship. The next rocket to go up was the Russian Proton M on March 12th. It sent a signals intelligence satellite into geostationary orbit, where, if it behaves like similar Russian satellites have, it will probably spend time in relatively close proximity to other countries' communication satellites in geostationary orbit. In the second of 2 Dragon-related activities this week, SpaceX launched the CRS-27 mission to the ISS on March 14th. The capsule assigned to this mission is completing its third flight into space and back. On board were 2,852 kilograms of science experiments and supplies, including a new carbon dioxide scrubber using capillary action, and some blueberries, apples, cherry tomatoes, and 4 kinds of cheese. Carbon dioxide scrubbers are typically restricted to use in full gravity, but a team from NASA Ames and a few universities have made a version that works in zero-G. It is hoped the technology will be used on future human spaceflights to the Moon and Mars. Another experiment going up on CRS-27 that caught the EVSN team's eye was a camera mount developed by high school students. A lot of us are photographers and know how difficult it is to get a steady shot. It's even more difficult in zero gravity. The students combined a commercially available monopod with a purpose-built 3D printed ball mount and a track segment for mounting lights. It's designed to stand on a ISS handrail for astronauts to take photos and videos of wherever they need, even in the middle of a module. The last experiment that caught our attention was the Tenpopo 5 experiment from JAXA, the Japanese Space Agency. It is designed to see what happens when bacteria and other living things are exposed to the harsh radiation of space. This type of research helps the study of the origin of life and the possibility of life elsewhere in the solar system. The samples will be exposed to space for 6 months and then returned to Earth for analysis. Also hitching a ride to space are a number of CubeSats, including 2 from NASA's Alana 50 mission, 3 from Canadian universities in Edmonton, Whitehorse, and Hamilton, 1 from the Aurora Research Institute, also in Canada, and 1 from the University of Stuttgart in Germany. Right before we recorded this episode, Rocket Lab sent up their second mission from U.S. soil, named Stronger Together. It was successful, and we'll have more details in the next Rocket News segment. Lastly, there was the Chinese Long March 2C on March 13th and a Long March 11 on March 15th. Not much is known about either launch, though we can tell you that the payload of the launch on the 15th was described as being used for, quote, land resource surveys, urban planning, disaster prevention and mitigation, and other missions. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the USA has had 20 launches, China 9, Kazakhstan 4, Japan 2, and India and the United Kingdom have each had 1. Of these 37 launches, there have been 3 failures, reminding us that space is hard.
Thanks, Eric. As you probably learned when you were younger, cooperation is an important part of life, and this is particularly true in space exploration, where cooperation is so important that it even takes precedence over politics when someone needs help during an emergency, or when you're trying to figure out how to tell time on the moon. At the end of February, the European Space Agency posted an article on their website talking about the challenges of keeping time on the moon. If humans are going to conduct regular missions on and around the moon, they're going to need to be able to communicate with each other and figure out where they are without the help of people who aren't on the moon, particularly if they're from different countries. And part of figuring out where you are is knowing when you are. Historically, lunar missions have kept their own mission times using chronometers, fancy mechanical clocks that are synchronized with chronometers on the Earth. This has worked because there haven't been a lot of missions on the moon, and the missions have tended to operate on their own. But with a lot of missions to the moon getting planned for the next decade and beyond, including large missions conducted in partnerships with multiple space agencies, it's time to come up with some definitions, which means it's time to form committees. Space organizations like NASA, ESA, and others are negotiating a new common architecture covering communications and navigation services on the moon known as LunaNet. They have a lot of work ahead of them, including answering the questions of who should be responsible for setting and maintaining lunar time, and should lunar time be kept synchronized with Earth or should it be set independently? And there is this little confusion created by relativity. Time actually runs a bit faster on the moon, and a 24-hour lunar day finishes about 56 microseconds before the same day finishes on Earth. Do we ignore those microseconds and just accept that atomic clocks will drift out of sync, or do we work to correct for them? I'm glad that folks are working to solve this problem before it actually becomes a problem, and I'm really glad I'm not on this committee. When we know what solutions are defined, we'll bring them to you here on EVSN. For now, though, just think about those 50 some odd microseconds a day. If you want to age slower than your sibling, you just need to send your sibling to the moon. That's all the science we have for tonight. We'll be back next week with all that is new in space and astronomy. For now, good night, and remember to go outside and look up.